Hello there, I'm Nigel Brewitt. I'm a part-time lecturer at Nottingham University Malaysia campus. I am dealing with some student groups in the second year of the mechanical engineering stroke mechatronics degree and assisting them in their design projects. This year it's a two-stroke engine. Now we've decided that we would take an old engine and strip it down bit by bit and video it, and I've created 2 videos now of that process. Come to the end of the last one, I wondered what was next, and so I decided to cut the engine in half, or should I say the cylinder head in half, and reassemble the engine to some extent in order to show the workings of the engine itself. So I can actually rotate it, move the piston up and down, showing how the relationship with the ports, etc. So I thought I'd use this video as a bit of a recap on what we've done before, and we'll go through the different components, identify the different components. We'll have a look at the process yet again, and we'll talk a bit about seals, and then we'll talk about the materials that are used in each of the components, and then the manufacturing processes that we would use in order to first establish a component, like casting or forging or whatever, and then take it all the way through to actually finishing the component. So with that being said, we shall get on with it. Okay, so let's start at the top, my pointer. Now in this design we're not bothering about the spark plug, of course. This is a multitude of materials which we don't need to concern ourselves with, but there's a spark plug, and it's creating a spark at this end into this chamber here, and that chamber is the piston chamber inside the cylinder head, which has all these cooling fins around it, and inside that cylinder head also you've got the exhaust port, the induction port, and if we take this down to top bottom dead center, you can see in the back there the transfer port as well. We'll talk about these a little bit more detail later. So obviously you've got the piston with its piston rings. This one's a slightly crown, got a slight radius to the crown. In your case you'll be using a flat crown. Now securing the piston to the conrod is the gudgeon pin, and you can just see there is a clip there which is called a retaining clip. It could also be a circlip. I'll just show you something about that. This is a brand new piston, and what we have here in the piston ring grooves is a little feature. And there's one in the top ring groove as well, and this prevents the ring from moving around too much. Don't forget, these rings have got a split in them to get them over these the crown into the ring grooves, and then we don't want them sliding around too much, although we do want them loose so that they can expand and contract as required. We've got grooves inside these holes there where the gudgeon pin goes, and the grooves here are for the retaining clip, which is either a wire clip, as in our case, or possibly a circlip. You've also got these cutouts here to allow access of fuel and air when this is in bottom dead center. So your fuel and air can still ascend through the transfer port. That's what these are for. And then the rest of it is a full skirt. So we have from the piston, we then have the conrod, and we refer to this end as the small end and this end as the big end. So and that attaches to the crank web via a crank pin, and inside there'll be the conrod surrounding a needle bearing which goes around the crank pin and is all secured together. All of this is press fitted together. So the crankcase is bolted to the cylinder head via this flange here, and these retaining screws just in the side here. So we need to talk about this space as well later on. Okay, so inside the crankcase you have bearings which are sitting in the back there, as you can see from this side more so, and also sat inside that is this, which is your lip seal, pushed in from the outside. So let's just go through the operation after identifying all the components. And at top dead center you can see we've got a gap here. This area here, you can imagine there's going to be a spark in this area. This helps for the distribution of that heat, this shape and everything, and then you've got this extra volume here which is a clearance volume, and this is called the squish. Now I've measured it on this one with using feeler gauges. These are feeler gauges, they're all different thicknesses, and it seems that the one that seems to fit best is the 40 thou, or in your case 1 millimeter. In the higher end engines, or the engines that they require for racing and everything, they try and minimize this distance so you've got greater compression, and they do that by taking out the gasket here between the cylinder head and the crankcase. That obviously brings this down. The stroke remains exactly the same, so therefore you are reducing this distance. You can't do it too much. There are limits, and I do not know them, but that is one of the things that they do in the higher level racing engine bracket. Okay, so the explosion takes place in this area here and drives the piston down to this point here where it interacts with the exhaust port. At this point here it has actually opened the exhaust port completely, and now, as you can see in the back, it has opened the transfer port as well. So bottom dead center then, the transfer port is fully open, and so is the exhaust port. Now the thing about this, an interesting thing that is normally done in this is the other half to this cylinder head, and you'll notice that the transfer port, this is the transfer, this is where it comes from the lower casing up to the above the piston. So the transfer port is actually angled in this direction, right? That direction being towards the induction port. Now it's not going to try and get out the induction port, but it is angled towards it. Now in this case it was the opposite. It's coming out of here into this area, this side of the chamber. So there's this action, this swirling action that's coming up and around here. And this actually assists in getting rid of the exhaust gases from this side and out through the exhaust port. So it's pushing the exhaust gases out the exhaust port. Obviously, when that happens, some fuel will be going out, which is why these are not exactly the most environmentally friendly engines. Okay, so as it ascends, you can see that the transfer port gets cut off and the exhaust port gets cut off, and it starts to compress the gas, and it gets to top dead center or close to top dead center, I think 5 degrees or so before the spark goes off, and then at top dead center it's fully compressed, and and the reaction takes place again. But when it's in this position, you can see that the induction port is now open, and it's now fully open, and it allows fuel air mixture from the carburetor into the crankcase, and in actual fact some of the cylinder head below the piston. Okay, when the piston descends through the chamber, it's actually squashing the fuel air mixture and forcing it up through the transfer port, which is right at the back here, and that's why they have this cut out in the thing to allow this to happen. It goes through the back, up through the port, into the piston chamber above the piston. Okay, so which brings us on a little point. I need to digress slightly here when we're talking about lip seals. Now, the lip seal is a very important part of the whole operation. It seals, as its name implies, around the crankshaft and the crankcase housing. So it fits around your crankshaft and the crankcase housing. It goes inside like that. So your crankshaft is going through this hole here. If that cracks, which it happens due to drying out, lack of use, it may crack. If it cracks, then it's got the possibility of letting air into this crankcase, which effectively is a sealed vessel, or indeed fuel out of the crankcase. So if we just take this as the piston ascends, you'll appreciate that the inside here there is a slight vacuum being developed. When it gets to the point here, there is the maximum amount of vacuum in here, and when it just opens there, it actually assists in sucking in the fuel air mixture that is being pumped in from the carburetor. So it's actually assisting in that. And when it's fully open, it is now sucked in and pumped in enough fuel into here for when the compression starts, or should I say the pressurization starts of the fuel, which forces it up through the transfer tube to above the piston. Now you can imagine if you have an air leak through your lip seal, the vacuum won't exist, or it will be greatly reduced. Therefore you would be relying on the pumping action of the carburetor, which is only through a small diaphragm, to deliver the fuel in the required time. So you could what they call run lean of that. You're putting less fuel in than you normally do, and therefore when you go through the cycle, you're introducing less fuel up here for ignition. Similarly, if you have a leak in your lip seal and the piston descends here through the chamber, it's actually pressurizing the fuel that's coming from the induction port, pressurizing it so that it actually forces it up efficiently through the transfer port to above the piston. If you had a leak here and the fuel was allowed to go out, then you wouldn't have any pressurization. Therefore, only a limited amount of fuel would come up through the transfer port, and therefore yet again you are running lean. So obviously, if you haven't got the fuel to burn, you're going to reduce your horsepower considerably, and eventually parts are going to just go and wear out. Not only that, you're not delivering lubrication in sufficient amounts to the rest of the engine, so that could have an effect on your bearings and your bearing surfaces. Okay, so that's the operation. I'm sure you're all familiar with that already, but I thought I would go through it. We've named all the parts here. Let's consider the materials that are used. The materials used in the spark plug we'll forget about because there are so many, from ceramics to brasses to steels to tungsten to nickel, all in the one unit. We'll concentrate mainly on the cylinder head and crankcase and the other parts, but you can imagine that in the cylinder head it's got to withstand a certain pressure, it's got to withstand the exposure to direct flame, and it's got to be reasonably wear resistant because the piston rings, the cast iron piston rings are going to be interacting with the piston chamber. So you could well imagine that this alloy could be quite a special alloy. Now, in some cases, in the high-end machines, the high-end racing machines, this could be titanium or titanium alloy, or magnesium, or indeed, like this is, an aluminium alloy. They're all alloys, by the way. No pure metals are used. So if we take titanium, it's terrifically high cost. Therefore, you wouldn't find it in this type of engine which drives a brush cutter. If you used aluminium alloy, it's a lot less cost. So you need to find an aluminium alloy that is got good casting capability. You also need to find one that's got this resistance to flame and friction and all these sort of things. So you need a bit more of a decent alloy here than, say, for instance, down at the bottom end, the crank case. So you most probably would require to get an alloy, and after the primary manufacturing process you may have to adopt a secondary process, and before you go into a tertiary process, which we'll talk about later. Down here on the crankcase you would only require a lesser alloy, but still an aluminium alloy because it needs to be light. This is a very cheap engine, so it's going to be aluminium, it's not going to be magnesium. But it doesn't need to have the same sort of properties as a cylinder head. So perhaps they're going to make this out of a cheaper alloy. Again, got to have good casting capabilities, but the properties, wear, pressure and all this sort of thing don't need to be considered so highly. So they may save a few cents. Remember, these things are manufactured in thousands, so they may find that they save a few cents by adopting a much cheaper alloy. Okay, so on the crankshaft itself, we need a bit of a better alloy, a bit of a more robust alloy. Here we can stand a bit of weight, really, because this acts as a bit of a flywheel. It acts as a balancing effect. It counterweights the rest of it, and so we can stand a bit of weight here. We also need to be a robust material, so you would go for a steel of a particular grade, and it'll be up to you to choose a grade, or a cast iron. So that's the material for the crankshaft in its entirety, because the crankshaft and the crank web are all the same really as far as requirements are concerned. So moving on to the conrod, notice on this one it's a slightly yellowy appearance. Now that suggests to me that this could be a bronze or a brass, and that is quite commonly used in this type of component. It's got reasonable characteristics as far as degradation to the atmosphere is concerned, because it is exposed to the atmosphere in various places, but it still has good stiffness, so that's probably why they've used it here. The piston we don't need to talk about, you don't need to design that, but it is an aluminium alloy, and the gudgeon pin will be made out of a steel yet again, and you consider the steel for wear characteristics as well as anything else. So that's the materials in basic for it. Let's have a look at the actual manufacturing processes that can be used. This, if you was a high-end alloy like a titanium alloy, it'd be very difficult to cast, and it's often machined. They go the extra mile with the precision of it because it's such an expensive material to make it out of. All of these cooling fins would actually be machined in the high-end more racing type bikes and things like this, but here we can cast it quite easily, and there's no need for that machining process at all. They can cast them very quickly, so and there's absolutely no need for anything required for a brush cutter or even some of the chainsaws and things like this, other than an aluminium alloy. In the bigger chainsaws, I might add, they do use magnesium alloys because the bigger chainsaws are rather heavy, so they try and reduce the weight by using magnesium. So you've got an alloy that you've cast and produced these features. Now, as far as the features go, some of the things you've got to remember is access of tooling. Here we've got a screw which attaches the cylinder head to the crankcase. Okay, that screw has got to get in there and it's got to get out as well. You've got to maintain this area, so you need access. So how do we get the tool in? Well, we cast some holes in here or cut these holes, these areas out to allow a tool to go through and down into the pin, the screw. Similarly, we don't want to lose the screw, so we don't want to try and drag it out through these holes. So we need some access here. So once we've unscrewed it, we can take it out with our fingers. So we've cut away, or should I say cast away, the fins, the lower fins here, to make that access. And this is commonly done. You need to make access for your tooling, and it's a big consideration when you're coming to the design and the aesthetics and all this sort of thing for it. So, okay, so that's the cylinder head. The crankcase itself, if it's going to be made out of ordinary aluminium alloy, choose a nice castable alloy, and you can, as I say, keep it somewhat cheaper than the cylinder head. Nothing special about the alloy, therefore subsequent treatments can be reduced as well. Right, so okay then, we've got the materials sorted out. What about the processes or the secondary processes? Just we've got some after you've done the casting, what next? Because after you've done the casting, this story just doesn't end there. We need to possibly heat treat this alloy in order to gain the properties that we require, wear resistance, strength, etc. For this component. We don't need to heat treat the crankcase. We don't need to heat treat this maybe, but this one, the steel used here, you may use a steel, you may use a cast iron. Now if you use a steel, what grade is it going to be? We need to consider what heat treatment we would need to give this its wear properties and its strength and fatigue resistance and all this sort of thing. So a secondary process is required for achieving the properties of things like the cylinder head and the crank shaft and crank web, etc. The material used for the conrod, by the looks of this, is a bronze type of material or a brass type of material, and it's got good stiffness. It gains its strength also by or possibly by a cold stamping or cold forging operation. Okay, so this can be stamped out or forged very quickly, hundreds a minute, this sort of thing. So there's no reason for anything special here. We just require it to be reasonably stiff. So you wouldn't make it out of aluminium, you would make it out of a bronze, or even a steel. You could make it out of a steel, there's no problem in doing that. But steel, you may have a little extra weight and everything, so you're trying to reduce that. The processing for the steel, if you're going to use hard wearing surfaces, then you could say that you need to case harden it. If you used a heat treatable steel, then you wouldn't need to do that. So you could use a cheaper steel and then case harden it, etc. One of the things that students do forget, and that is that casting something doesn't mean to say it's finished, and neither does the processing for the material properties. You still need to have that final machining process to produce the surfaces that you require for good operation. So you would not leave this bore as a cast finish. It would be machined to make it nice and smooth, so you reduce the friction of your cast iron rings. The surfaces here require machining for balancing. The surfaces here require machining for holding bearings, or to be able to slide into bearings and have a nice fit with bearings. You need to cut the threads on this as well. You also need to consider cone fittings like this with a woodruff. It all needs machining to a nice surface finish. Again, the threads. It's a tapered finish. There'll be a tapered hole in the flywheel with a keyway, which matches. You'll match up or align with the woodruff keyway here, and with a little key, you press it in. You'll press it onto this surface, and you'll squash it onto the surface by using a nut here and squashing it onto that surface. So we have our engine with the materials identified-ish, the processing identified, ish, and the final machining identified ish. So you've got to decide what grades of materials you require. You've got to decide what sort of processing you're going to do on it. You've got to decide what sort of machining operations are you going to carry out, and by which method. So would you turn this? Would you mill it? What would you do? So you've got to decide on those, but you can use these processes, and I'm sure you'll be able to easily recognize which was required where. Don't forget, all these surfaces would require finish machining. This one, even in the crankcase has got to house these steel pins. These are press fitted into the casting, so they've got to be precision machined as well. Each of these has got to be threaded, these fastening holes. So there's quite a lot of finish machining done. It may be done in a very productionized way and a very quick way, but it does still need to be done. So okay then, that would conclude my talk about the two-stroke engine, its operation, its components, its materials, its processing, its machining, and I hope that has given you some type of instruction. Well, I hope that was of some use to you. We've covered most of the aspects of the engine, so I'm quite pleased with that. Here's hoping that you've gained a bit more of an assimilation with the two-stroke engine process, and hopefully you've gained a bit of knowledge as far as materials and manufacturing process is concerned. So all that remains is to wish you well. Thank you very much.